Right now, 26,000 light-years from your seat, at the very center of our galaxy, lurks something so monstrous that even light, the fastest thing in the universe, cannot escape it. Sagittarius A star is a supermassive black hole with a mass equivalent to 4 million suns. It doesn't glow, it doesn't make a sound, it just sits there, in absolute silence, slowly devouring everything that gets too close. Stars, gas, dust, time, all disappear beyond an invisible boundary of no return. But what if we had a ship? Not just a ship, but a machine capable of surviving the journey, or at least transmitting data before it ceased to exist. What would we see? What would we feel? And most importantly, what would happen to our bodies, to our time, to reality itself as we approach the point where the laws of physics cease to apply? Today, we'll take this journey step by step, from a safe distance to the event horizon itself and beyond. Get ready, because what physics predicts will be stranger than any science fiction. Before we set off, let's understand what a black hole actually is. Forget the movie image of a giant vortex in space sucking in everything around it. A black hole is neither a hole nor a vortex. It's an object. More precisely, an unimaginably dense object that has compressed its entire mass into a point of infinitesimally small size, which physicists call a singularity. Around this point, space-time is curved so dramatically that beyond a certain distance, the speed required to escape exceeds the speed of light. This distance is called the event horizon. Not a physical surface, but a mathematical boundary beyond which information is no longer accessible to an outside observer. Anything that crosses the event horizon remains within forever. Black holes come in many different sizes. Stellar black holes, the remnants of massive stars that collapsed under their own weight, have masses ranging from a few to tens of solar masses. Their event horizons are tens of kilometers in diameter. Supermassive black holes, such as Sagittarius A star at the center of the Milky Way, or M87 star in the Virgo galaxy, contain millions or billions of solar masses. The event horizon of M87 star is larger than our entire solar system. M87 star became the first black hole to be imaged in 2019 by the Event Horizon Telescope project. A dark silhouette against a hot disk of gas and plasma. To obtain this image, 8 radio telescopes scattered across the planet from Hawaii to the South Pole were combined into a single virtual Earth-sized telescope. The data collected in a single night of observations amounted to 5 petabytes, so much so that it was faster to transport it on hard drives by plane than to transmit it over the internet. The result, a fuzzy orange ring around a black spot, became one of the most important images in the history of science. For the first time, humanity saw something that was, by definition, invisible. In 2022, the same project captured an image of Sagittarius A star, the black hole at the center of our own galaxy. It turned out to be significantly smaller than M87 star, but no less impressive. For our thought experiment, we'll choose a supermassive black hole, and here's why. Small black holes have monstrous tidal forces near their event horizons. The difference in gravitational attraction between your feet and your head would be so enormous that you'd literally be torn apart long before crossing the horizon. Physicists call this process spaghettification, and it's exactly as terrifying as it sounds. But supermassive black holes have such large event horizons that the tidal forces at their boundaries are relatively weak. You could cross the event horizon of Sagittarius A star without even noticing, at least at first. This is what makes supermassive black holes ideal candidates for our thought experiment. So, we're on the ship, the engines are running, the coordinates are set. We're beginning our approach. Stage 1, the distant approach. The distance is several light years from the black hole. At this distance, the black hole is completely invisible. It emits no light, but you notice its presence through indirect signs. The stars in the background behind the black hole shift slightly. Their light is bent by gravity as it passes by the invisible object. This is called gravitational lensing. The black hole acts like a giant lens, bending light rays around itself. If you were to look directly at the black hole, you would see a characteristic effect, an Einstein ring, the light from distant stars bending around the black hole from all sides and converging into a glowing ring. It would be a mesmerizing sight, a thin, glowing hoop in the void. At this distance, you're still completely safe. You can feel the black hole's gravity, but it's no stronger than the pull of an ordinary star. Your clock is running normally. Your body feels fine. The only thing unusual is the sky. It's starting to look a little strange. The stars behind you, in the direction you came from, appear slightly bluer. The stars ahead, in the direction of the black hole, appear slightly redder. This is the Doppler effect. As you gain speed, falling into the gravitational field, the light ahead is compressed, while the light behind is stretched. The effect is barely noticeable yet, but it will soon become much more dramatic. Stage 2. The accretion disk. The distance is several hundred event horizon radii. If our black hole is active, meaning there's matter falling in around it, one of the most spectacular spectacles in the universe unfolds before you. The accretion disk is a flat ring of gas, dust, and plasma orbiting the black hole at nearly the speed of light. Friction between the disk's layers heats the matter to millions of degrees, causing it to emit X-rays and gamma rays. If your eyes could see across the entire electromagnetic spectrum, the accretion disk would shine brighter than 1 billion suns. A striking fact: black hole accretion disks are the most efficient energy sources in the known universe. When matter falls into a black hole, it converts up to 40% of its mass into energy. By comparison, thermonuclear fusion at the center of the Sun converts less than 1%. This is why quasars, the nuclei of distant galaxies with supermassive black holes actively devouring matter at their centers, shine brighter than all the stars in their host galaxy combined. Some quasars emit as much energy as 1 trillion suns. And all this from a region of space no larger than our solar system. Many active black holes emit relativistic jets from their poles, streams of plasma accelerated to 99% the speed of light and extending for thousands of light years. The mechanism by which these jets form is not fully understood, but magnetic fields swirled by the rotating accretion disk are thought to play a key role. If our ship were to encounter a jet, it would result in instantaneous annihilation, a stream of particles with energy exceeding anything Earth-based accelerators can generate. But even in visible light, the spectacle is stunning. The disk doesn't look what you expect. Due to the monstrous curvature of space-time, light from the far part of the disk bends around the black hole and becomes visible from above. At the same time, light from the lower part of the disk bends around it from below. As a result, you see not a flat disk, but something resembling a hat, a glowing band wrapped around a dark sphere from several sides simultaneously. This effect was precisely calculated by physicist Kip Thorne and brilliantly visualized in Christopher Nolan's film Interstellar. The film's rendering of Gargantua is one of the most scientifically accurate depictions of a black hole in cinematic history. There's another detail that makes the disk appear asymmetrical. The part of the disk moving toward you appears significantly brighter than the part moving away from you. This is relativistic amplification. The light emitted by matter moving toward you at near light speed is compressed and amplified. The opposite side, on the other hand, dims. The disk appears as if one half is glowing white, while the other is barely smoldering. This effect is called relativistic beaming, and it transforms the symmetrical structure into an asymmetrical, almost lifelike spectacle. At this distance, the first noticeable relativistic effects begin to appear. If you could contact someone on Earth, or anyone far from the black hole, you'd notice something strange. Their clock is ticking slightly faster than yours. Or, from their perspective, your clock has slowed down. This gravitational time dilation is a direct consequence of Einstein's general theory of relativity. The deeper you dive into a gravitational field, the slower time appears to you compared to an outside observer. For now, the difference is minimal, a fraction of a percent, but it will increase exponentially. Stage 3. The photon sphere. The distance is 1.5 Schwarzschild radii from the center of the black hole. The Schwarzschild radius is essentially the radius of the event horizon for a non-rotating black hole. For a black hole with a mass 10 times that of the Sun, it is about 30 kilometers. For Sagittarius A star, it is about 12 million kilometers, which is about 17 times the distance from the Earth to the Sun. The photon sphere is one of the most exotic zones in the vicinity of the black hole. At this distance, gravity is so strong that photons, particles of light, can move in a circular orbit around the black hole. The light literally orbits it, like a satellite orbits the Earth. If you were suspended on the photon sphere and looked straight ahead, you would see the back of your head. Your own light, having circled the black hole, would return to you. In theory, you could see multiple copies of yourself. Light can make several revolutions before being deflected. Of course, it's impossible to hang on the photon sphere. The orbit here is unstable. The slightest disturbance will send you either outward or inward, toward the event horizon. But the very concept of a place where light travels in a circle demonstrates how monstrously warped space-time is near a black hole. At this distance, the sky looks completely alien. The black hole in front of you now takes up a significant portion of your field of view, not as an object, but as a region of absolute blackness, surrounded by a thin rim of distorted light. The stars behind you are still visible, but their images are distorted beyond recognition, stretched, smeared, and displaced. The entire universe, if you could turn around, would appear as a shrinking, glowing ring above you, as if you were looking up from the bottom of a well, with the stars crowded at its edge. Gravitational time dilation is already significant here. Every hour on your watch corresponds to several hours for a distant observer. If you spent a day here and somehow returned, significantly more time would pass on Earth. Recall the movie Interstellar. 1 hour on the planet near Gargantua was equivalent to 7 years on the ship. This isn't science fiction. It's the mathematics of general relativity. Stage 4. Approaching the event horizon. Distance is measured in units of Schwarzschild radii. You're falling. Your thrusters won't help. Stopping would require infinite energy. Space-time around you is so warped that the very concept of outward begins to lose its meaning. All directions, including spatial ones, gradually veer toward the singularity. You haven't yet crossed the horizon, but escape is already virtually impossible. To an outside observer, someone watching you from a safe distance, something paradoxical occurs. They see you slowing down. Your ship, approaching the event horizon, appears slower and slower. Your image turns red. The light you emit is stretched by gravity, shifting it into the red and then into the infrared part of the spectrum. From their perspective, you will never cross the event horizon. You will freeze at its edge, gradually fading until you become invisible. To them, your fall into the black hole lasts an eternity. This isn't an illusion or a trick of the eye. It's a fundamental property of space-time. Time flows infinitely slower near the event horizon compared to a distant observer. If you could hover a few centimeters from the event horizon for a minute and then miraculously return, thousands, millions, or even billions of years could pass on Earth, depending on how close you were. A black hole is a time machine that only works in one direction, into the future. But for you, it's a completely different story. Stage 5. Crossing the event horizon. And here it is, the moment we've been waiting for. The event horizon, the point of no return, the point beyond which even light cannot escape. What does it feel like to cross it? Nothing. Absolutely nothing. This is perhaps the most counterintuitive fact about black holes. The event horizon is not a wall, not a membrane, not a force field. It's a mathematical boundary, invisible and imperceptible to anyone who crosses it. Einstein's equivalence principle states that a free-falling observer cannot distinguish gravity from the absence of gravity. As you fall, space-time around you appears locally normal, and no detector will detect the moment of crossing. The only way you'll know you've crossed the horizon is by one sign. You can no longer send a signal outward. But since the signal travels at the speed of light and you travel slower, you can't even verify this in real time. But here we encounter one of the greatest unresolved paradoxes in theoretical physics, the black hole information paradox. In 1974, Stephen Hawking demonstrated that black holes are not completely black. They slowly evaporate, emitting what's known as Hawking radiation. This is a quantum effect. At the event horizon, particle-antiparticle pairs are born from the vacuum, one of which escapes while the other falls in. the black hole loses mass and eventually, after an unimaginably long time, evaporates completely. But where does the information about everything that fell into it go? Quantum mechanics asserts that information cannot be destroyed. General relativity asserts that everything beyond the event horizon is forever cut off from the outside world. These two assertions contradict each other, and resolving this paradox is one of the great unsolved questions in modern physics. The answer may require a completely new theory, quantum gravity, that combines quantum mechanics and general relativity. Stage 6. Inside the black hole. You've crossed the horizon. You're inside. What next? This is where physics gets truly weird. So weird that our language and our intuitive understanding of space and time break down. Inside a black hole, space and time reverse their roles. This isn't a metaphor, it's a mathematical fact, a consequence of the solutions to Einstein's equations. Outside a black hole, you can move in any direction in space, but only forward in time. Inside a black hole, the radio coordinate, the distance to the singularity, becomes time-like. This means that moving toward the singularity is as inevitable as moving forward in time. The singularity is not a place in space, but a moment in the future. You can't escape it any more than you can escape tomorrow. All paths, all directions, all trajectories lead to it. As you approach the singularity, the tidal forces increase. For a supermassive black hole, they were weak at the event horizon, but now, closer to the center, they become monstrous. The difference in gravitational attraction between your head and feet, even if the distance between them is only 5 feet, begins to increase exponentially. Your body is stretched vertically and compressed horizontally. This is spaghettification, the process by which any object is stretched into an infinitely thin thread. To understand the scale of these forces, imagine standing on the surface of the Earth and gravity pulling on your legs slightly harder than on your head. The difference is about 1/10,000,000th of the total force. You don't feel it. Near a black hole singularity, the same difference can be trillions of times greater than the force binding the atoms in your body. At first, you'd feel a slight, uncomfortable stretch, as if someone were pulling on your legs and head at the same time. Then, increasing pain. Then, muscles, tendons, bones. Then molecules, atoms. Ultimately, even subatomic particles would be torn apart by tidal forces. Everything you are made of would be transformed into a stream of elementary particles falling toward the singularity. The entire process, from the first sensation of discomfort to complete destruction, would probably take a fraction of a second on your own clock. But since time inside a black hole behaves unpredictably, even this statement is only a rough estimate. What is a singularity? It's a point at which the density of matter and the curvature of spacetime approach infinity. According to general relativity, a singularity is a place where volume is zero and density is infinite. But most physicists believe this isn't a description of reality, but a signal that the theory breaks down. Infinities in physics usually mean we're using the wrong model. What actually happens at a singularity is anyone's guess. It's terra incognita for modern science. Perhaps quantum effects prevent compression to infinite density. Perhaps a singularity isn't a point, but some kind of quantum structure. Some theories suggest that a singularity could be a portal, a passage to another region of space-time, to another universe. But this remains speculation. There's another type of black hole that makes the story even more interesting. A rotating black hole, described by the Kerr solution. Most real black holes rotate because the stars from which they formed rotated. A rotating black hole's singularity is not a point, but a ring, and mathematics allows for the possibility of passing through this ring without colliding with infinite density. Where does this ring lead? The equations predict an exit to another region of spacetime, perhaps to another universe, or to another point in our own. This is the so-called Einstein-Rosen bridge, or wormhole. But most physicists are skeptical of this possibility. The internal structure of a real, rotating black hole is likely unstable and prevents passage. Let's step away from physics for a moment and talk about scale. Black holes aren't some exotic rarity. They're everywhere. Astronomers estimate that our galaxy contains between 100 million and 1 billion stellar black holes. Nearly every large galaxy has a supermassive black hole at its center. The recently discovered black hole, TON 618, has a mass of 66 billion solar masses, one of the most massive known. Its event horizon is so vast that our entire solar system could fit inside it several times over. Black holes shape galaxies, regulate star formation, and possibly play a key role in the evolution of the entire universe. And now, we have a way to hear them. In 2015, the LIGO detectors detected gravitational waves for the first time, ripples in spacetime predicted by Einstein exactly 100 years ago. The signal was the result of a collision between two black holes, each roughly 30 solar masses, over 1 billion years ago. In a split second, they merged, releasing the equivalent of 3 solar masses of energy in the form of gravitational waves that rippled through the universe and caused detectors on Earth to shift 1,000 times smaller than the diameter of a proton. Dozens of similar events have been detected since then. We live in an era when, for the first time in history, humanity can not only see the universe, but also hear it. And the voice we hear most often is the voice of colliding black holes. Finally, black holes teach us how little we know. Every aspect of our journey, gravitational time dilation, spaghettification, the information paradox, singularity, is a window into fundamental questions we don't yet have answers to. What are space and time at their deepest level? Can information be destroyed? Do other universes exist? Black holes aren't just exotic objects somewhere far away in space. They are laboratories where nature experiments at the limits of the possible, experiments whose results we are only beginning to decipher. They challenge our understanding of space, time, causality, and the very nature of reality. And perhaps that is precisely their greatest significance. Black holes show us where our knowledge ends and where territory yet to be discovered begins. If you were to actually make this journey, from the distant approach to the singularity, you would travel from the familiar physics of everyday life to the limits of human understanding. You would see space morph into time, light move in circles, the entire universe collapse into a luminous ring above your head. You would experience, if only for a few moments, an experience untapped by any living being in history. And in the final moment, before tidal forces rip apart every atom of your body, you might glimpse something no theory can predict. Something that lurks beyond infinity. Tell us in the comments which part of the journey struck you the most, and subscribe to the channel because the universe is full of objects even stranger than black holes. See you there.